Chapter 13 Magnetic Effects of Electric Current. Electric current produces magnetic effect. We know that the two effects produced by an electric current are heating effect and magnetic effect. Having learnt about heating effect, let us understand the magnetic effect of electric current by performing an activity. Activity. To perform this activity, we require a battery, a switch, a straight thick copper wire, a magnetic compass, and few connecting wires. Connect negative terminal of the battery to the switch. Connect the other terminal of the switch with a wire. Similarly, connect another wire to the positive terminal of the battery. Now we have two free ends. Label them as X and Y. Connect the copper wire between the points X and Y. Now, horizontally place the compass near the copper wire connected between points X and Y. Close the switch. What do you observe? You observe that the needle is deflected. Now, open the switch. What do you observe? You observe that the needle comes back to its original position. Let us now understand why does this happen. We know that a compass needle always sets itself in north-south direction. The deflection in a needle from its usual north-south direction is possible only when it is acted upon by magnetic effect of another magnet. This shows that an electric current produces a magnetic effect due to which the needle gets deflected. If an electric current flows through a conductor, it sets up a magnetic effect around the conductor. This effect was discovered by scientist Ørsted. Let us know more about him. During some experiment, he noticed deflection of a compass needle when an electric current from a battery was switched on and off. He discovered that electricity and magnetism were related phenomena. Magnetic field and magnetic lines of force.
We know that when unlike poles of two magnets are brought close to each other, they attract each other. Whereas like magnetic poles repel each other. However, this interaction, that is, attraction as well as repulsion between like and unlike magnetic poles or between magnet and magnetic substances is observed within the specific region surrounding the magnets. It is because the magnet exerts its influence within that specific region only. This region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field. Let us now perform an activity to understand the concept of magnetic field in detail. We need a glass, few U-pins, a magnet and some water to perform this activity. Take a glass filled with water. Add a few U-pins into the glass. Now try to take all the U-pins out from the glass with the help of a magnet. Keep it a little away from the glass. Now, bring the magnet near the glass very slowly. You can see that as the magnet moves nearer to the glass, the U-pins move towards the magnet. The U-pins stick to the surface of the glass as the magnet is brought very close to the glass. Now, move the magnet in the upward direction in contact with the glass. You will notice that the U-pins are also pulled upward along the inner side of the glass. Hence, we observed that when the magnet was far away from the glass, it could not attract the U-pins, but when it was kept closer, it could attract the U-pins. This region around a magnet in which a magnet can attract iron by its magnetism is called the magnetic field.
Magnetic field has both magnitude as well as direction. The direction of magnetic field at a point is indicated by the north end of the needle of a compass when it is placed at that point. Let us now plot the magnetic field pattern due to a bar magnet using iron filings by performing an activity.
Take a bar magnet, a drawing board, a white paper, and some iron filings. Put the white paper on the drawing board. Keep the bar magnet at the center. Sprinkle few iron filings on it. Now, tap the board gently. What do you observe? You will observe that the filings have oriented themselves around the magnet, crowding at the poles.
Let us now understand why do the iron filings arrange themselves in a specific pattern. We know that the magnet exerts its influence, that is force, in a space surrounding it. Due to this force, iron filings arrange themselves in a pattern. The lines along which the iron filings align themselves represent magnetic field lines. Let us now perform an activity to obtain the magnetic field lines due to a bar magnet by using a compass.
Take a drawing board and fix a white paper on it using drawing pins. Place a bar magnet at the center and draw its outline using a pencil. Now, take a magnetic compass. Let us place the compass near the north pole of the magnet. What do you observe? The needle gets deflected and the north pole of the needle points in a particular direction. Mark a point on the paper at the tip of the north pole. Now, place the compass needle such that the compass needle's south pole points towards this point. Mark another point on the paper at the tip of the north pole. Continue this till you reach the south pole of the bar magnet. Join all the points by a smooth line. A line starting from north pole always ends on the south pole. Hence, magnetic lines of the force are always closed lines, emerging out from one pole and entering the other pole. Repeat this for different starting positions of the needle. You will see lines emerging out from one pole and entering the other pole. At poles, the lines are crowded and are far separated near the middle of the magnet. These lines are called as magnetic lines of force. Let us study their properties. Magnetic lines of force. The path along which the unit north pole moves in a magnetic field is called magnetic line of force or magnetic field line. Some of the properties of magnetic lines of force are: magnetic lines of force are closed and continuous curves. They start from north pole and end on the south pole. The tangent at any point on the magnetic field line gives the direction of the magnetic field at that point. The magnetic lines are crowded where the field is strong and far from each other where the field is weak. The magnetic lines of force never intersect each other.
Let us understand that why do two magnetic field lines never intersect each other. Place a magnetic compass at the intersection point of two magnetic field lines P and observe deflection of magnetic needle. You will observe that the magnetic needle comes to rest only in one direction. This shows that there cannot be two different directions of the magnetic field at one place. That is, two magnetic field lines never intersect each other. Magnetic field due to a current-carrying conductor. We have learned that when an electric current is passed through a conductor, it produces a magnetic field around it. But what about the direction of magnetic field produced? Let us understand it by performing an activity. To perform this activity, we require a battery, a switch, a long straight copper wire, a magnetic compass, and few connecting wires. Connect the negative terminal of battery to one terminal of switch. Connect the other terminal of the switch with a wire. Similarly, connect another wire to the positive terminal of the battery. Mark the free ends of wires as X and Y. Place the compass between these points. Now, connect the straight wire between points X and Y in such a way that it is parallel to the compass needle resting in north-south direction. Close the switch and observe the deflection of needle. You observe that the needle deflects towards the east. Now, open the switch and replace the battery connections to reverse the direction of electric current. Do not disturb the position of switch, compass and straight wire. Close the switch and observe the needle. You observe that the needle deflects towards the west. This implies that when the direction of current flowing through a conductor is reversed, the direction of magnetic field produced due to it also changes. Magnetic field due to a current through a straight conductor. The pattern of the magnetic field generated by a current through a conductor depends on the shape of the conductor. The magnetic field pattern produced due to straight current carrying conductor is different than the magnetic field pattern produced due to a circular loop carrying current. Let us understand first magnetic field pattern due to a straight current carrying wire in detail by performing an activity.
Activity: take a rectangular cardboard and pass thick copper wire through its center. Connect a battery, an ammeter, a plug key, and a rheostat in series with the wire. Here, rheostat is used as variable resistance. Sprinkle iron filings uniformly on the cardboard. Insert the plug key and tap the cardboard gently. What do you observe? The iron filings have arranged themselves in circular patterns of varying radius. Now, increase the current flowing through the wire by adjusting the rheostat. You will observe that the filings get crowded in smaller circular patterns. Bring a compass close to the wire. You will observe large deflections of the needle as the compass is moved towards the wire. If the current in the wire is increased, the compass needle is deflected more, indicating greater strength of the magnetic field.
Right-hand thumb rule.
The magnetic field produced at a point due to a current-carrying conductor is directly proportional to the magnitude of the current passing in the wire, inversely proportional to the distance of the point from the wire. The direction of the field produced at a point is given by right-hand thumb rule. It is observed that reversing the direction of the current reverses the direction of deflection of the compass needle. The direction of the magnetic field is given by right-hand thumb rule. This rule states that if you imagine yourself holding a current-carrying conductor in your right hand, that the thumb points towards the direction of the current, then the curled fingers around the conductor will give the direction of the magnetic field.
The right-hand thumb rule is also called Maxwell's corkscrew rule. According to Maxwell's corkscrew rule, imagine driving a corkscrew in the direction of current, then the direction in which we turn its handle is the direction of magnetic field lines. Magnetic field due to a current through a circular loop. Let us now perform an activity to understand the magnetic field pattern due to a circular loop carrying current.
Activity: take a rectangular cardboard with 2 holes and a coil of number of turns of a conducting wire. Insert the coil through the holes such that the turns are normal to the cardboard. Connect the coil in series with a battery, a key, and a rheostat. Sprinkle some iron filings uniformly on the cardboard. Insert the plug key and tap the cardboard gently. What do you observe? You will observe that the iron filings get arranged in a pattern. What does this indicate? This indicates that a magnetic field is developed due to the current flowing through the circular coil. The filings get arranged in circular pattern with the wire of the coil as the axis. What do you observe if the amount of current is increased by adjusting the rheostat? You will notice that the filings get arranged in circular patterns of smaller radii, indicating increase in the magnitude of the magnetic field. Let us study the magnetic field due to a current through a circular loop. We have seen that the current flowing through a circular coil produces a magnetic field. We can find the direction of the field using the right-hand thumb rule. Hold the wire in the right hand such that the stretched thumb points to the direction of the current, then curled fingers will give the direction of the magnetic field. Hence, the magnetic field lines are concentric circles. Imagine 2 diametrically opposite small elements of the coil. Draw circles with increasing radii concentric with these elements. The circles or magnetic lines at the center of the coil are compressed, making them crowd along the axis of the coil. Similarly, considering the effect of all the elements of the coil, we find that the magnetic field due to the circular coil is axial. The magnetic field produced by a current-carrying wire at a point depends directly on the current passing through it. Therefore, a coil with n number of turns will produce magnetic field n times larger than that produced by a coil of a single turn. This is because the field due to each turn adds up as the current in each turn flows in the same direction.
Let us now perform activity.
Activity: take an insulated wire, a nail and a dry cell. Wind the insulated wire tightly around the nail in the form of a coil. Connect the free ends of the wire to the two terminals of the dry cell through plug key. Now, bring iron pins close to the nail. What do you observe? You will observe that the pins get attracted to the nail. Now, remove the key. There is no current flowing through the wire. The pins are no longer getting attracted to the nail. If we insert the plug key once again to the cell, the nail attracts the pins once again. Repeat this process of connecting and disconnecting the cell and observe the pins. This activity shows that a magnet can be produced by passing current through a coil. This type of magnets produced using electric current are called electromagnet. Let us find how a magnetic field is produced due to a current flowing through a solenoid.
Magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid.
When an electric current is passed through a solenoid, it produces an axial magnetic field. The current flowing through a circular coil produces an axial magnetic field. Hence, the magnetic field produced by a solenoid is also axial, forming south pole at one of its end and the north pole at the other end. Outside the solenoid, the magnetic field lines travel from north pole to south pole. The end of the solenoid having clockwise circulation of current in the transverse view forms the south pole, while the other end, where the current can be viewed to be flowing counterclockwise, forms the north pole. Does this field resemble the magnetic field produced by a bar magnet? Yes, this leads us to conclude that a solenoid has all the properties of the field produced by a bar magnet. The magnetic field produced in the core of the solenoid is uniform.
Let us now draw the magnetic field inside a current-carrying solenoid.